here we need to compute the derivative of this function for a constant a. And I come to you now and I claim that in order to cook up this derivative, we need three ingredients, namely the chain rule, the linearity of the derivative, in the sense that the derivative of the sum is the sum of the derivatives, and the derivative of a to the x. So if we know these three things, then definitely we can find a solution. And if you have not, then you are highly encouraged to retry the problem now that you have these hints with you. So we start with the derivative of ln a to the x plus a to the minus x. I hope it is clear that this is a composition of functions. So I hope you don't mind if I actually write this as ln of x composed with a to the x plus a to the minus x. And of course, this is what I'm taking the derivative of. So if I'm taking the derivative of a composition of functions, there's an outer function and an inner function. So what happens is you take the derivative of the outer function, you plug in the inner function into the derivative that you just found, and then you multiply by the derivative of the inner function. So in our case, this would be f, and this would be g. So we need to find f prime. And maybe there's a fourth fact that you need to know, and that is the derivative of ln of x is 1 over x. So that's another piece of knowledge you should know. And understand, of course. So this can be proven in a certain way. And it is good practice to know at least where this is coming from and why it makes sense. In this case, if you want to prove it, you can prove it using the derivative of the inverse function of ln of x, which is e to the x. But that's a topic for another video. So the derivative is the derivative of this whole thing is going to be equal to the derivative of the outside function, which is 1 over x. And then I compose it with my inner function. That's something I still need to do. And then I need to multiply by the derivative of the inside function, which is a to the x plus a to the minus x. So here on the side, I'll compute this very specific derivative. I hope I do not forget to put this dash as in derivative. In this equation, we apply the chain rule, if that is not clear for you. And now here, we will apply the second property, and that is the derivative of the sum is the sum of the derivatives. And then I apply the third one, which tells me that a to the x prime is a to the x times ln of a. This is something you can prove using using implicit differentiation. So you would let y be equal to a to the x, and you would take the natural logarithm both sides, and then you have something that looks like this, and then you differentiate both sides and solve for dy by dx. And this is precisely, if y is equal to a to the x, then dy by dx is d by dx of a to the x. And that's how you do it. But that's of course a topic for another video as well. I just don't want you to feel like I'm telling you, hey, this is number 1, this is number 2, this is number 3. You need to memorize them, and this is how it's done. This is actually not how it's done. So that's what I do not want to convey. These are simply reminders. But it would take a lot of time if I would like to prove every single statement I use. That's why I dedicate this for in other times. So I dedicate other times for this. Okay, so the derivative of a to the x is a to the x times ln of a. And similarly, the derivative of a to the minus x will be a to the minus x, but you need to multiply by the derivative of the inside function. So here we're applying the chain rule. And the derivative of the inside function minus x is minus 1. So here I'll just put a minus. And that's very good, because now it remains to compose this 1 over x with a to the x plus a to the minus x, which gives me 1 over. So composing just means that I remove x and I put in whatever I have for the other function. That's what it means. Just like this. And I multiply by the derivative, which is given as follows. Now I believe there's some simplification that could be done, but in my opinion I think this is good enough to be accepted as a solution.